Hi, Zach McKinney here with Team 16 with Brandon Ward, Keith Snyder, and Eric Bentley. We've all made it into 489 and we're all still on track to graduate on May the 6th. So we're excited to get back into the semester and get it done. We actually spent some time over the break working on our project so we could bring the material side of our project to a conclusion. Brandon and Keith will talk to you about some of the technical details here in a minute. And then Eric's going to talk to you about our schedule and how we're going to finish all of our deliverables on time, get everything turned in, and be ready for presentation day, which is in less than 100 days now. So with that, I will turn it over.
Thank you, Zach. My name is Brandon. I'm going to go over the hardware that we've landed on. We decided on the particle photon. Seems to be working pretty good for us, better than some of the stuff in the past. And the fact that it sends data to the cloud and it's so easy to get that data out of the cloud basically makes the particle photon something we want to stick with and go ahead and use as our device. So I'll go over how we've got it connected and what it's doing and some of the challenges that we've had. So right here you can see the basically just have this velcro to the wall here, and we've got our power cord coming in. It's just a generic 5-volt AC adapter that's powering the photon. The photon is gathering the CT signal through this thermostat wire, through our voltage dividers and CT burden resistor. And then we've got the CTs here. We did have some challenges. Not every one of us is using the same CTs, but these are the cheap ones that work. But you can see here I've had to put a zip tie on them and just to make sure that they're tight and the magnets are touching. Otherwise you don't get a good signal from the CT, and if you don't get a good signal you can't tell what's running, and you know, this is the basis. The better CT we have, the more accurate data we're going to be able to acquire and be able to more accurately do it. But this is a DIY project, so these are working very well. So that covers the hardware. I'm going to turn it over to Keith, and Keith can go over the script and everything on how we're getting this into something that we can look at.
All right, thanks for the demo, Brandon. My name is Keith Snyder, and I'm going to give you a quick demo of the back end of our project. Like Brandon mentioned, one of the great things about the particle photon is that it's a cheap device that's cloud connected right out of the box. Our project is going to involve storing and processing a lot of data, and we've looked at several different solutions for data, such as hosting the data at a web server on the device itself, or offloading onto something like a Raspberry Pi with an SQL database. But what we've landed on is using the particles Photon's cloud functionality to push the data directly into a Google Sheets spreadsheet. The advantage of using a spreadsheet is that it's simple, free, and most people have worked with spreadsheets before and are pretty familiar with them. Also, Google's built a pretty impressive scripting language that allows you to automate a lot of the data management in the spreadsheet. So a quick reminder of our project's workflow. We have a particle photon that Brandon showed you. It's monitoring the Holmes current signature on each phase. It's calculating the RMS current, doing an FFT on the waveform to analyze it, and then sending all of that data to the Google spreadsheet. So here what you see on the video is what the Google spreadsheet looks like that's receiving the data. You see in column A we have a timestamp. Column B will be the RMS current on the A phase. Over here we have B phase. And then we see the first 10 harmonics, 60 hertz, all the way 120, 180, up to 600 hertz, the magnitudes of those frequency for each phase here. So if I scroll all the way to the bottom, you can see new data coming in. It's coming in about every 6 seconds. We've played around with the frequency a little bit there, and 6 seconds seems to be about as quick as we can get it to update before we start running into problems. We can tab over here and see what a plot looks like. Here, the blue line here is actually the RMS current. Up here, the red line is your 60 hertz magnitude, and then as you go down, you can see the code on the right, different frequencies. So our theory is that when different appliances turn on, they'll affect the different frequencies in different ways so that we'll be able to identify when they've turned on. To give an example of what a dashboard could look like, Here we can see several appliances: well, water heater, microwave, furnace. See our data coming in. This is about the last 2 hours of real-time data. We'll see the current in leg A and leg B. When we scroll down a little bit here, we can see where, for example, the well turns on. We have some green lights there, and other appliances coming on as well. Here goes the microwave turning on. So we're keeping all of this data in real time. At the end of the day, we have a Google Sheets script which archives it. For example, and this is a separate document here, but it's got my last 7 days, all the data from the last 7 days. It also keeps a running list of just the, not all of the data, but just the total kilowatt hours for each day, phase A, phase B total, and then the cost based on local power rates. Here's an example of just a summary of the last week, how much money was spent. And what we're working on right now is a script that can, at the end of each day, crawl back through all of the data. And based on, here, we're going to show you these appliance signatures. These are 3 appliances that I've gotten the signatures for. This is how much each one changes when it turns on. So for example, the microwave turns on, no change on the A phase because it's 120 only. It's over on the B phase, and each of these columns is going to go up by about this amount. Same with the coffee maker. Oven, it's on both phases there, 240 volts. So at the end of the day, the script, it crawls through for each appliance on that appliance signature page, crawls through each line of this 18,000 lines here, looks at the change in magnitudes, compares it, and if it's within a certain tolerance of that, it decides that it's on and tells how many kilowatt hours it used in that, and this is the total kilowatt hours for the whole day. So that's where we're at now. We're working on refining that script, making it better at appliance identification. I'll now pass it on to Eric for our conclusion. Thanks.
Thanks, Keith. I'm briefly going to touch on where we're at with the budget and the schedule moving forward into the semester. As far as both those items are concerned, we are on time and under budget, which is where we want to be for any project. Budgetarily, we wanted to remain under $100. We were at that $100 mark for a while, and then recently with the removal of the Raspberry Pi from the equation, we're standing at about 10% of the cost of similar products on the market. So this being a DIY project, keeping the cost that low is obviously a very good thing. So I will pull up the Gantt chart and take a look at that. Some key dates we have coming up. Well, here we are right at January 20th, ready to turn in video 1. Towards the middle of February, we have 2 key components that we should have completed. The ability to set up new appliances within Google Sheets, and the most important part of the project, calculating power and estimating dollar cost for what you're spending to have a particular appliance on. And then as we move towards the end of February, getting more of the administrative portions of the project done, diagrams, and getting the step-by-step instructions ready to upload to GitHub so that we can have the DIY community take a look at it and see what they think. And then going from there, between the 15th of March and April, update the documentation as needed depending on the feedback from the user base. And then moving all the way down to graduation, which we're all very excited about. So I think that'll about do it for Team 16 and Video 1. I appreciate your attention, and we look forward to the rest of the semester. Thanks.